At the end of the last lecture, I set you a problem which was to determine whether or not the three vectors v1, v2 and v3, which I've written at the top there, were linearly independent as elements of R cubed. So what you need to do in order to solve this problem is to find out whether there exist three numbers, real numbers a, b and c, not all 0, such that a times v1 plus b times v2 plus c times v3 is equal to the 0 vector. If you can do that, if you can find these three numbers, not all of which are 0, then the vectors v1, v2, v3 are linearly dependent. Otherwise, they're linearly independent. And this really is just a problem in which you need to solve some simultaneous equations, because if you write down a times v1 plus b times v2 plus c times v3 is equal to the 0 vector, and if you collect the terms on the left-hand side into a single vector, this is what you get. So you have three simultaneous equations in the three variables a, b and c. And what you want to know is, what are the solutions for a, b and c? Or in particular, are there any solutions in which not all of a, b and c are 0? And if you solve that however you like, you might just guess a solution, or you might instead form the augmented matrix and put it into row reduced echelon form. However you do it, you'll find that there are some non-zero solutions to those simultaneous equations. For example, a equals 1, b equals minus 2, c equals 1 is a solution. And of course, none of those are 0, so it's certainly true that not all of them are 0. So v1, v2, v3 is linearly dependent. It's not linearly independent. Okay, here's our new concept for this lecture. It is the concept of the span of some vectors. And I'm reminding you at the top here of a definition we saw last time, because we need to use it again, which is the definition of linear combination. If you have a vector space V and some elements of V which are written v1 up to vn, then a linear combination of those vectors v1 up to vn is simply an element of the form a scalar times v1 plus a scalar times v2 plus a scalar times v3 up to a scalar times vn. So any element which can be written like that is a linear combination of v1 up to vn. We're now ready to make our new definition, which is that of a span. So if you have an F vector space V, so that means F is some field and the scalars which you're allowed to multiply it by in this vector space come from the field F. And if you have some elements v1 up to vn in V, then the span of v1 up to vn, which we write like this, is by definition the set of all linear combinations of v1 up to vn. So here's the same definition in symbols. The span of v1 up to vn is written is by definition the set of all linear combinations that you can make of v1 up to vn. So let's take a quick look at an example of the span of some vectors. So we'll work in R squared as usual. So this contains two vectors, 1, 0 and 0, 1. Let's look at the span of those two vectors. So I'll give these some names. This is going to be v1, this is going to be v2. Then the span of v1 and v2 is by definition the set of all linear combinations of v1 and v2, where the scalars come from, in our case, the real numbers, because we're talking about a vector space R squared, which is a vector space over the real numbers. So this will be all the things of the form x times v1 plus y times v2, where x and y are real numbers. All right, well, we can simplify that a little bit. We know what v1 and v2 look like, so actually x times v1 plus y times v2 is just the vector x, y, where x and y are in R. Okay, that's the whole of R squared. So in this particular case, the span of our two vectors v1 and v2 was equal to the whole of R squared. Let's now do another example. So we're just going to look at a generic example where we look at the span of one single vector. So we're going to take V to be a vector space and V, little v, to be a single element of V. And we're going to ask what is the span of little v? Well, it's the set of all linear combinations of the one vector little v. And a linear combination of just one single vector is just a scalar multiple of that vector. So if v is a vector space, let's say over the field F, then what this looks like is the set of all things of the form L times V for L in F. So if you like thinking geometrically, then in the special case where let's say V was equal to R cubed, and V, little v, was some single vector x, y, z, like this, then, well, span V would be a line through the origin. It's the line through the origin consisting of all scalar multiples of x, y, z. So a line in three-dimensional space, R cubed. A straight line through the origin. The origin means the zero vector, 0, 0, 0. Okay, one more example there. Now, this is more of a special case of this definition. So we define, for technical reasons, it sometimes turns out to be useful to define the span of the empty set, so no vectors. The span of the empty set is defined to be the zero subspace of V. So just the set containing the zero vector in V. Okay. Every example of a span we saw there turned out to be a subspace of the vector space. And that's no coincidence. Spans of elements are always subspaces. So we're going to prove this on this slide. We'll prove the proposition which says that if you have elements S1 up to Sn of a vector space V, then their span is a subspace of V. And I've copied at the bottom there the definition of a subspace in case for some reason you've forgotten it. So let's do a proof of this proposition. All right, and of course we have three things to check when we verify something as a subspace. So let's, for the sake of saving me from having to write it out every time, let's give this thing a name. We'll call it capital S, like this. And our job is to prove that S is a subspace. And if I want to prove something as a subspace, then what I have to do is check the three conditions in the definition of subspace. So first of all, I have to show that S contains the zero vector. So S here, the span, let's remind ourselves of the definition. The definition is it's the set of all linear combinations. So let's say sum from I equals 1 up to n of Li times Si, where the Li's are elements of the field F, over which V is a vector space. Okay, well, does it contain 0? That's what we have to check when we're doing the first part of our proof. Well, it does contain 0 because we can simply take all of the L's to be 0. So S contains 0 times S1 plus 0 times S2 plus, and so on, up to 0 times Sn, which is, of course, the zero vector. So, condition 1 in the definition of being a subspace, is satisfied by S. Right, let's do condition 2. Condition 2 is about closure under addition, so I have to take two arbitrary elements of S and prove that their sum is in S. So what do elements of S look like? They look like linear combinations of S1 up to Sn. So we can write those in summation notation just to make it a bit quicker to write. We could have one arbitrary element looks like the sum of Li times Si, and another element might look like the sum of Mi Si. Let those things be elements of S. We've got to prove that their sum is also in S. So the sum of the Li Si's plus the sum of the Mi Si's. Okay, but in a vector space, you can do all the ordinary manipulations with vectors which you would do with column vectors. In particular, what you can do is just collect the terms in S1 and S2 and S3. So just by rewriting these sums in a different order, which you're allowed to do because addition in a vector space is associative and commutative, and by using the distributivity property, what you can do is just rewrite this as the sum of Li plus Mi times Si. But what you've got here really is a linear combination of the Si's. This is some scalar, some element of our field F over which V is a vector space. So this is a linear combination of S1 up to Sn. So it is an element of S, right? And we're done. We've shown that a sum, any sum of two elements of S is also an element of S, which means S is closed under addition. So we have the final thing to check, which is closure under scalar multiplication. Let's do that. So we have to pick an arbitrary element of S, which we know can always be written as a linear combination sum of Li times Si. And we have to pick a scalar. So let's call that A in the field F over which V is a vector space. Then what we have to show is that A times our element of S is in S. Well, what is that? We can simplify this. We have our vector space axioms. Vector space axioms tell you you can always distribute a scalar multiplication over a sum. So in particular, you can write this as the sum of I equals 1 to n of A times Li Si. And of course, I have another property of scalar multiplication, which is one of the vector space axioms. I can rewrite that as A times Li, where I do that multiplication in my field F, multiplied into the vector Si. Alright, that is a linear combination of S1 up to Sn. So it's an element of S. Right. S contained the zero vector. S was closed under addition. S was closed under scalar multiplication. So it is a subspace of V. Next, we're going to make a definition of spanning set, and here it is. We say that elements V1 up to Vn of a vector space V are a spanning set for V if their span is equal to V. There's actually another piece of vocabulary which we use. So we either say these elements are a spanning set, or we might say V1 up to Vn spans V. But those things mean exactly the same, which is that the span of V1 up to Vn is equal to the whole vector space V. And you have already seen an example of a spanning set. So example, what we saw earlier was that the span of the vectors 1, 0 and 0, 1 in R squared was all of R squared. So these two vectors, let's give them names, E1 and E2. E1 and E2 is a spanning set for R squared. Okay. Let's look at a trickier example. So how about vectors V1 which is 1, 1 and V2 which is 1, minus 1. So the question we're going to ask is, are these a spanning set for R squared? Do they span R squared? So in other words, what we're asking is it the case that span of V1 and V2 is equal to R squared or not? Well, certainly the span of V1 and V2 is a subset of R squared. So the question is just, is this span all of R squared? So you might like to think about this. Maybe pause the video, try and figure out what you need to do. Well, if you did that, then well, let's now work out the answer. So the answer is yes, it is a spanning set. But if we want to figure this out, what we have to do is to say, can we write every single vector in R squared as a linear combination of V1 and V2? So we're asking, is it true that for every x, y in R squared, we can write that vector as a linear combination of V1 and V2. In other words, there exist real numbers a and b in R such that a times V1 plus b times V2 equals xy. Right, you have to be able to solve this, so to find a and b. So given any x and y, you have to be able to find an a and b to make this true. So the answer is yes, as I just said. Because you can do this, again, this is just a matter of solving linear equations. Because if you just collect together those two vectors on the left, we need to, what you have is a plus b and a minus b on the left. So this has a solution. No matter what x and y is, there is a solution. A equals x plus y over 2 and b equals x minus y over 2. So no matter what x and y is, no matter what x is and what y is, you can always find a solution for a and b. This is such a solution. So every vector in R squared is equal to some linear combination of V1 and V2, and that means the span of V1 and V2 is the whole of R squared. Now if you had a harder problem, so a larger problem with bigger vectors, it might be a bit harder to get a solution. Right here, because we've just got two simultaneous equations and two variables, you can just do this by playing around with the equations by hand. But if you had more equations and more complicated larger equations, you can still do this because you know how to solve systems of linear equations. You've got your methods of row-reduced echelon form, which will allow you to do this. So let's do a more complicated example. We're going to take an example in R cubed. So this time we will take U1 to be 1 minus 1, 0. U2 to be equal to 0, 1 minus 1. And U3 to be equal to 1, 0 minus 1. And we're going to ask well, let's put this another way. Do U1, U2 and U3 span R cubed? Okay, to put it another way, is it true that every element of R cubed can be written as a linear combination of U1, U2 and U3? So that's what you need to be able to do. For any x, y, z in R cubed, you need to be able to find scalars a, b and c in the real numbers such that a times u1 plus b times u2 plus c times u3 is equal to that vector x, y, z. And let me emphasize, you have to be able to do that for absolutely any vector x, y, z in R cubed. So, well, can we do it or not? You should try and solve this now. Pause the video and try and solve it. Okay, I hope you did this. So I'm now going to try and show you how you can solve this. So the first step to do is to collect the vectors on the left of this equation into one single vector. And if you do that, you will get A plus C at the top, then minus A plus B, and then minus B minus C, like this. And this is equal to x, y, z. You want to know whether or not this system of three linear equations in the variables a, b and c always has a solution no matter what x and z, y and z is. So let's say I don't know how to do this. Let's say I can't tell just by looking at it. Well then I remember all the things that I learned about row-reduced echelon form, and I write down the augmented matrix for the system of linear equations a plus c equals x minus a plus b equals y minus b minus c equals z. So that augmented matrix is 1, 0, 1, x, 0, 1, 1, x plus y, and 0, 0, 0. Oh no, it isn't. I've got that wrong. I'm jumping ahead of myself. Let me write this more carefully. What is it? 1, 0, 1, x minus 1, 1, 0, y, and then 0, minus 1, minus 1, z. This is the augmented matrix. For the system of linear equations, a plus c equals x, minus a plus b equals y, minus b minus c equals z. So this is the column corresponding to A, this is the column corresponding to B, this is the column corresponding to C, and this last column is the column corresponding to the constants. So that first row represents A plus C equals X, the next row represents B minus A equals Y, and so on. Okay, you know what to do next. You do row operations to put this thing into row-reduced echelon form. So I'm not going to write all those out, but if you do these row operations, then here is what you will get. So actually I'm not going to go all the way into row reduced echelon form. I'm just going to do some row operations, and if you do just a couple of row operations, here is what you get. So if I add row 1 to row 2, and then if I add the new row 2 to row 3, here is what you get. And now you can see straight away that there are going to be some cases where there are no solutions to this system of linear equations, because you can now see that if x plus y plus z is not 0, then what we've got here is a system of linear equations where the last equation is 0 equals something which is not 0. So if x plus y plus z is not equal to 0, then the row reduced echelon form is 1, 0, 1, x, 0, 1, 1, x plus y, 0, 0, 0, 1. And you can see there you have a leading entry in the final column. So the last equation is 0 equals 1, and there are no solutions. So for some values of x and y and z, it is impossible to write the vector x, y, z as a linear combination of u1 and u2 and u3. That means that the span of u1 and u2 and u3 is not all of r cubed, because, for example, it doesn't contain 1, 0, 0, because then the sum of the entries of that vector is not 0. So this is not in the span of u1, u2 and u3. They are not the spanning set.